All right, let's make sure that this is recording as well. Okay, so hello again, everyone. We are going to get started. Hopefully everyone can hear me, and we are good to go. So I'm pretty sure we're going to be keeping this same setup because Zoom is, so be sure when you enter, I guess, I can probably set this, but be sure when you enter the meeting that you mute your mic, because otherwise everyone can hear you, and yeah. So I'm pretty sure, all things considered, I'm going to stick with Zoom, like forget Blackboard Collaboration Ultra at this point. We're just going to continue with the setup we have here. I'm still actually working on kind of syncing the video on Zoom with the video in the camera, but I think it can actually work out with my camera, but I think I need extra equipment to get it to work. I need like certain HDMI cables and stuff and converters and things of that sort. And as you can imagine, Amazon and all these other places, they're not delivering these things very quickly at this point. So still working on that. In the meantime, hopefully this is good enough. We will have two different angles here, as well as, I don't know if you guys, when you participate, you automatically have access to the links to download all this stuff. If not, someone remind me to send the links later on. Okay, so this is where we left off last time. Hopefully you actually tried this stuff. Let's just talk about a little bit about last time. So last time, one of the main things we covered was the idea of a Taylor series. Of a function f of x. This was assuming, of course, we could take multiple derivatives. In fact, we could take we can take the derivative of f of x an infinite number of times, and the derivatives behaved nicely, they were continuous, and they didn't get too big. Then we could define something called the Taylor series of a function as this guy, n goes from 0 to infinity, of f to the nth derivative evaluated at x naught over n factorial times x minus x naught to the n. And this was known as the Taylor series centered at x naught. So centered at x naught. And we also spoke about something called the Maclaurin series, which is what I asked you about here. And the only thing that a Maclaurin series is, it's really just a Taylor series centered at 0. And so if I wanted to find a Maclaurin series for a function, I would write it as n goes from 0 to infinity of f to the nth derivative evaluated at 0 over n factorial times x to the n. And this was a way to write, both of these are ways to write a function as an infinite polynomial, which we spoke about last time. These guys were called power series in general, and the Taylor series is just one method to develop the power series of a function that you might not know about, well, what that would be beforehand. So we have these two ways of actually talking about a function as a power series. Now, technically, I haven't justified to you that we can think of a function as being equal to this guy. I'll talk a little bit about that today. Kind of in a hand-wavy way, your textbook goes into the proofs or why we can say this is equal and under what conditions you can say that it's equal. I'll tell you what the conditions are, but I'm not going to actually justify to you what those are. If you're interested in that, you can actually just read the textbook. But you should be fine without it. So there are going to be situations in which we can think of a function as being identically equal to its Taylor series, and we're going to get a lot of good things coming out of that. But in the meantime, let's just focus on being able to actually calculate such a series for these functions. we are also going to find the radius of convergence and interval of convergence, which we all know you always use the ratio test to get that done. You always use the ratio test to get that done. Yeah, so we are going to do this. So I'll do the hardest one. This is the one for e to the x, and then I'll have you guys take a crack at cosine of x. The sine of x is actually going to be very similar, so I'll probably just tell you the answer to that one when we get there, but let's actually get through the first one. So the idea is overall not so complicated. Basically all we're going to do is just try to apply this formula, namely, specifically because I asked for the Maclaurin series. I'm going to try to apply this formula to these functions. So here's how we would go about doing it. Let's do the first one.
Yeah, looks like I'm have to.
Come again? Someone ask a question? So that should be in your notes from last time. So now let's actually just apply those formulas. So let's look at the function f of x equals e to the x. We want to find its Maclaurin series. Now there's a formula. Let's just keep it in the corner here. So this is the series n goes from 0 to infinity of f to the nth derivative at 0 over n factorial times x to the n. So we want to find this guy for that function. So what do? Well, remember the original function, this is the 0th derivative. Right, so we haven't taken any derivatives yet. So I know what f to the 0 of x is. What I do need to know is what it would be evaluated at 0. So I'm just going to plug in f of 0. And if I plug in f of x equals 0 here, I would get, well, 1. The next thing I'm going to do is I'm going to want to find the first derivative, f prime. Now the derivative of e to the x is, of course, e to the x. And that's someone coming in. And if I evaluate the derivative at 0, well, I get 1 again. If I go the second derivative, this is going to be, well, e to the x. And that again gives me 1. Now, what you would do here in general is you want to do enough derivatives so that you kind of see a pattern forming, and I can kind of tell you right here what the pattern is. The nth derivative is going to be e to the x, and that would mean, of course, f to the nth derivative at 0 is going to be 1. Right? So this part is the important part here. So for e to the x, I want to, in general, just find what does the nth derivative evaluated at 0 actually look like. And for this particular function, it's always 1. And so what I can do is I can then take this value and plug it in to that formula. So this implies the Maclaurin series for f of x equals e to the x is series n goes from 0 to infinity of, just going to plug in 1 over there, 1 over n factorial times x to the n. Now that I can rewrite as this guy. And that's your answer. Now, if you've been paying attention, you would have seen that guy already. You'll notice that that was actually one of the examples that we worked on in the last class. Is this a question? Oh, well, I just showed my faculty ID. It's definitely close to students. So someone asked how I got on campus. Pretty much told them I'm a faculty and I'm going to be by myself. I'm obeying the distance rules and all that good stuff. And eventually they let me in. So I'm all by my lonesome. There's pretty much no one here. I think the custodians come in later on, but they start cleaning and they kind of leave me alone. So, yeah. So that's the guy. This for e to the x, I can write as this series. And again, you'll notice that is a guy that we've seen before. And I've actually mentioned this to my Calc 1 class like a few seconds in Calc 1. Oh, this is another way to think of e to the x, and no one knew what I was talking about. Well, now you know what I'm talking about. This is a way to write e to the x as a series.
Professor?
Yes.
So, you know how you did e to the x, first derivative? Did you do the second derivative on the second one? Because I'm seeing it's just f to the 1 prime. Is that supposed to be double prime?
So this is f prime here. Then I do have double prime here.
You put only one dash into it, where you put f to the f prime 0. If you go.
Oh, this is supposed to be double prime.
Oh, okay.
Yeah. So pretty much you find enough derivatives so that you can kind of see a pattern for the coefficients. Because you kind of want to know what would this coefficient look like in general. Once you figure out what that is, you just literally plug it into this formula. And so that's our e to the x. Now, what we need to do, well, I can actually just kind of cheat here and use the fact that we actually found what the radius of convergence and interval of convergence of that guy is last time. The radius of convergence equals infinity, and the interval of convergence equals minus infinity to infinity for the above. So, in some sense, and again, this is something I have to justify a little bit later, instead of the function e to the x, which we all know and love, we know that's the exponential function, we know its graph and all that good stuff, we can actually think of this as an infinite polynomial. I can, in some sense, think of e to the x as, well, 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus going on forever. I can think of this infinite polynomial as being e to the x. And again, I'm going to kind of talk about under what conditions we can actually say this, but that's the start of it. And more or less, we know that this way of thinking of e to the x will work pretty much everywhere. On the entire real line, at any point that I want to examine e to the x, instead of examining e to the x, I would be able to examine this infinite polynomial, which inherently will have a lot of nice properties that I can take advantage of. And I can examine this guy in many ways a lot easier than I can examine that guy. We'll talk about that a little bit later as well. But yeah, so now what I would like you guys to do is do the same for cosine. So I'll do the usual, I guess give you guys 5 minutes to try this out. Here's the formula. I'll write that down for you. Now in general, by the way, this formula is something that I would expect you to memorize. I'm not going to actually give this to you when the time comes. Right? But that's the formula you want to apply, and you want to figure out if your f of x is the cosine function. How would you go about finding that guy? So try to go through the same process I just did with the exponential. Cosine is going to be a little bit trickier, but it's the same principle in general. And once you do that, find the Maclaurin series of this guy. I will give you guys 5 minutes to take a shot at that. So everyone try it, let me know what you kind of get. Don't look it up, actually try to do it. It's easy to look it up, it's easy to Google it. It's a very famous series. but actually try to work it out, because there are going to be times where I'm going to ask you to do this for unfamiliar functions, and so you need to know the process. About 2 more minutes left. Okay, I have about 30 seconds left. right, someone chime in here. Tell me what you did. It's your cue. It's you. Well, it doesn't have to be you specifically, but if you wants to chime in, you can chime in.
All right. So I just took the first few derivatives of cosine.
Okay.
So for the first derivative, it's x.
Minus sine. How many derivatives did you take?
4. Isn't the derivative cosine sine? Because you have minus sine.
It's the derivative of cosine is minus sine.
Oh.
Yeah, yeah. We've been doing so many integrals. The integral of cosine is positive sine. The derivative of cosine is minus sine. And then the derivative of the sine function is going to be the cosine. The derivative of cosine is minus sine, which with that negative makes it so positive. And the fourth derivative is going to be, well, cosine. And you can imagine that this is actually going to repeat, right? Because we've gotten back to the cosine. So whatever pattern we need to find, we can find it from these first 4 derivatives. After that, the pattern is going to repeat. Okay, so we have the first 4 derivatives. We have these guys. What did you do next?
Then I evaluate it at f of 0. So you get 1, 0, minus 1.
Which is 1. F prime of 0 is 0. F double prime of 0.
That should be minus 1.
And F triple prime of 0, that's going to be 0. And F to the 4th prime of 0 is 1. And that is just going to keep repeating. So it goes 1, 0, minus 1, 0, 1, 0, minus 1, 0, 1, 0, minus 1, 0, going on like that forever. So if you were to tell me a pattern for f to the n evaluated at 0, how could you do it?
It should be minus 1 to the n.
Okay.
Or were you asking for something else completely?
Well, well, for the 0 derivative, that definitely does work. But that does not work for that's not going to work for the others. So something is off here. So that's not going to work. Not by doing that. Other ideas? Because you definitely see an alternating sign with the 1s here. But just throwing in a minus 1 to the n, those zeros are going to mess up the pattern. So any ideas on how to maybe I'll give you a hint here. So this guy happened at the 0th derivative, right? So in the series, this is going to be the term you would get when n equals 0. This will be the term you get when n equals 1. This will be the term you get when n equals 2. This will be the term you get when n equals 3. This will be the term you get when n equals 4, so on. Does that help you come up with a pattern?
I have no idea because I kind of like once I did that part, I just wrote out the sequence and then like or just wrote out like the pattern, substituting the different values of like n from 0 to whatever until I saw a pattern, and then I just kind of came to a conclusion about what the
Yeah, I
series
see
should
it.
be.
Huh? Someone else wants to chime in on how we could get this pattern going? Because the zeros kind of mess up the -1 to the n thing. If you wanted to do the -1 to the n, who are the guys who obey that pattern?
All the even ends.
All the even ends. You'll notice here, this one, this one, this one, and so on. So n equals 5 is going to ignore the pattern, n equals 6 keeps the pattern, n equals 7 ignores the pattern, n equals 8, and so on and so forth. The even ones behave like -1 to the n. These guys here behave like -1 to the n. So in other words, you could say here that your f to the n evaluated at 0 really behaves in two different ways. It will give you a 0 when your n is odd, and it will give you a -1 to the n when n is even. Or there's a nicer way to actually say that. Well, let's write that down in a nicer way. So basically what we're saying is note I don't remember, did I tell you guys how to represent even and odd? So let me do that first, because that's going to be nicer. Note, I already wrote note. If k is an integer, we know k is odd if we can express k as 2n plus 1 for some integer. While k is even. So we call things odd and even by, if they look at it this way, if k equals just 2n for some integer n. So basically what I can say is every time I'm hitting a subscript that looks like 2n, an index that looks like 2n, it's going to behave like -1 to the n, and everywhere else at the indexes of 2n plus 1, it's going to behave like 0. So given that, here's what we can say. For even n, for the even terms, we will behave like -1 to the n. And we can ignore the odd terms since they give us 0. And if we're adding zeros, we can just forget about it because we're adding zeros. here's how we're going to look at the cosine. N goes from 0 to infinity. So now, I know this is I want it to behave like -1 to the n. But how do I make sure that it will only work for the even guys and I ignore the odd guys? Well, instead of putting n factorial in the denominator, I'm going to force it to work for the even factorials. Namely, I can put here 2n instead of n factorial. And for the x to the power, I only want it to work for the even power. So to force that to work, I can put 2n. Now, if you notice what's going to happen here, if my n equals 0, this is 0. If my n equals 1, this is 2. If my n equals 2, that's 4. If my n equals 3, that's 6. If my n equals 4, that's 8, etc. 2n is just going to output all the even numbers. Now, once I'm outputting an even number, I want the nth derivative to behave like -1 to the n. So notice that when n equals 0, it's going to give me a 1. If n equals 1, it's going to give me a -1. If n equals 2, it's going to give me a, and so on and so forth. This way I can force the pattern to work on the even ones by replacing the n's with two n's. That is because that's how we can think of an even number. And I mentioned this to a lot of you. I don't remember if I mentioned this to you guys. But these are ways you can think of odd and even numbers. And so that's actually the Maclaurin series for cosine. And I can write it out so you can see it, i.e. Now, if you were to write this out, what it would look like, if I plug in n equals 0, I would get 1. If I plug in n equals 1, I would get minus x squared over 2 factorial. If I plug in n equals 2, I get plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial, plus x to the 8th over 8 factorial, minus dot dot dot. Notice this only forces the even guys to show up when n equals 0. It'll look like the original formula where n equals 0, 2, 4, 6, 8. So I'm only getting the evens, and on the evens I'm getting an alternating sign. So I use the -1 to the n to give me that alternating series pattern, but I only force it to work on the even numbers by just making the guy that's counting up an even integer by always doubling it. Oh, someone said modulus. Well, yeah, if we're essentially doing 0 mod 2, if that helps anyone. Yeah. So it means I can think of cosine, and again we're going to justify this, as this infinite series. It'll only work on the even numbers. Now for all the odd numbers, you can think of them as being there, but they're actually going to give you zeros for the coefficients. So there's really a 0 x to the 1 over 1 factorial, and then there's a 0 x to the 3 over 3 factorial. But all the odd numbers, they just hit zeros. So I just completely ignore them, like don't even worry about it. Just alternate on the even numbers, and that is going to be your Maclaurin series. Now, by the way, this is just something you should know, but I'll actually write this down in a little bit. I'm going to talk about all the power series and the Maclaurin series that I expect you guys to know by heart. So that being said, tell me how to find the IOC and ROC. So, this is my power series. How do I find the radius of convergence and the interval of convergence?
like the ratio test?
Ratio test.
That?
Always the ratio test. Yeah. So by the ratio test, what is the ratio test? What are we going to set up for the ratio test? L equals the limit of
The n+1 version of that multiplied by the reciprocal of that series right there.
so what's the power going to look like?
It should be 2n plus 2 or 2n.
2n plus 2, right?
Yeah.
Because you change all n's to n plus 1s, so you have to distribute the 2. It ends up being x to the 2n plus 2 over 2n plus 2 factorial. Then I'm going to multiply by the reciprocal of that guy. So it's 2n factorial over, well, x to the 2n. Well, times the minus 1 to the n. Now, we can start canceling some things here. This goes into that. This guy will go into that part. So I'm left with an x squared there. How can I simplify 2n factorial over this guy? What would that become?
The 2n plus 2 factorial is basically 2n plus 2, 2n plus 1 times 2n factorial.
Right. So this guy cancels into that guy, but it leaves this part left over. So ultimately now what we have is the limit in absolute values. There's going to be a minus 1, but of course we can ignore that minus 1 because we're taking absolute values. We're going to be left with an x squared, and then we're going to have all of that divided by 2n plus 2 times 2n plus 1. And what's that limit?
0.
0. What's so special about 0? Well, it's less than 1 always. What does that tell us about this thing? What's
the ROC is infinite?
right? Radius of convergence is infinity because it will work for any x. It does not matter what x is, no matter how large a number I plug in for x. This limit is going to approach 0, and so any x is going to work. So it turns out that this Maclaurin series converges absolutely on the entire real line. Now, similarly, we can show your sine of x function. Let's write it this way, the Maclaurin series for sine. Is n goes from 0 to infinity. You'll notice that if you did the sine, it's going to behave very similar to the cosine. So your f of x is sine, your f prime is going to be positive cosine, your f double prime is going to be negative cosine, blah, blah, blah. The same sort of pattern is going to ensue, except your sine and your cosine are returning the opposite signs. It's going to be like shifted. So what you're going to notice is going to happen, it's going to have that minus 1 to the n pattern, but it'll only have it for the odd numbers this time. And all the even numbers would give you 0. And so what you can do is write this as 2n plus 1 factorial and x to the 2n plus 1. That forces the alternating sign pattern to take effect only for odd numbers. And this has, very similarly, it's going to look very similar to this one. So this will also have an infinite radius of convergence, and its interval of convergence is the entire real line. This has ROC equals infinity, and IOC as well. Any questions on that? I mean, you might have to go over the calculations very slowly, but if anyone's completely lost about some step I took, now's probably the time to stop me. That being said, here is a list of Maclaurin series that I would expect you to know. And by no, let's put down no in uppercase letters here. Right. So when I write no in uppercase letters, what that means is you should both be able to derive them as well as know them by heart. You're never going to have to derive these specifically, but you need to know the process of how they were derived because you might want to apply that process to other functions. And I'll be asking you that. So, one function that we looked at, and this wasn't in this lecture, this was in maybe 2 lectures ago, we looked at the function 1 over 1 minus x, and we saw that we could write that as a series of just x to the n. We also saw that this guy has a radius of convergence of 1, and the interval of convergence was strictly between -1 and 1. Next thing, we saw e to the x. We saw that today. We can think of this as the series n goes from 0 to infinity of x to the n over n factorial. This guy has radius of convergence infinite, and interval of convergence, the entire real line. We also saw that the cosine function, I can think of it as, and yes, I still have to somehow give you the justification for these equal signs, but in the meantime, just know that you can kind of think of these two things as equivalent. So for the cosine, it's -1 to the n, x to the 2n over 2n factorial. This guy also has radius of convergence infinity, and the interval of convergence is the entire real line. We then have the sine function. This we can think of as the series n goes from 0 to infinity, -1 to the n, x to the 2n plus 1, divided by 2n plus 1 factorial. This guy has radius of convergence infinity, and interval of convergence -infinity to infinity. So, these are 4 things that we just know now. We know what these are. Like, these have to be memorized. So, like, by the next time I see you, you should have all of these series memorized. You should be able to regurgitate this off the top of your head. You should know that 1 over 1 minus x, I can think of it as this series. The series from n goes from 0 to infinity of x to the n. There are a couple ways to do this. One, you can think of this as a geometric series where your a is 1 and your r is x. It's going to converge absolutely once your absolute value of x is less than 1 in absolute value. Another way is you could actually do the Maclaurin series using the form that I gave you. The f to the nth derivative, you're going to realize is actually going to be n factorial. Your n factorials are going to cancel out, which that will actually be a nice exercise to try. If you want something unfamiliar to actually figure out, try to actually do this the Maclaurin series way. We did it with the geometric series test last time, but try to actually do the Maclaurin series way for this guy. And you'll notice that the f to the n derivative evaluated at 0 is going to actually give you n factorial. So it cancels out the n factorial and you're just left with the x to the n. This guy here we just derived, this guy we just derived. That guy is very similar to this guy, so I didn't derive that, I just stated that. But these, you have to know all of these. You have to actually know by heart each of these functions, what their corresponding Maclaurin series are, and where these Maclaurin series actually work. Okay. So give you some time to copy that down or take a snapshot or whatever. Okay, so these are just guys we know now. I'm thinking of what I want to do next. Do I want to just tell you about when this all works first before going into applications? Yeah, if I'm following the textbook, yeah. So pretty much everything we know now would bring you up to section 10, I want to say 10.8 in the text. So maybe let's actually stick with the order that the textbook goes into and talk about 10.9, where most of 10.9 is just some concepts that you should be aware of. It's not going to be the source of any calculation or method that we're going to use. But in 10.10, we're going to actually do some applications. So yeah, so let's talk about it's about convergence of Taylor series. So like I said, we're just kind of going to rush through this. I just wrote down some facts that I want you guys to kind of know in the background. I'll probably never directly test you on this stuff, but it's some things that you would want to know, and especially those of you who are going on to be like math majors and things of that sort. Things where you actually need to understand math a little bit more than just the computational side of it. These are actually important things to actually worry about. No, you don't have to know the power series for a tangent by heart. So no. But I will say this. You should be able to derive something like the power series for a tangent inverse. Right, so that would actually be a pretty good test question. Maybe I'll put that like on a mock test or something like that. So I could ask you a question something like, oh, use a known power series to find the power series of that, or to actually find the Maclaurin series of that using the method. So tangent inverse is something that you should actually know, believe it or not. You don't have to know it by heart, but because it's actually not that hard to actually derive it. The hint would be to know that the derivative of tangent inverse is 1 over 1 plus x squared. And you can actually use the Maclaurin series in part A to actually figure out the power series for the tangent inverse. So that's something. So the tangent function itself, no. I'll never ask you that, and you won't have to memorize that. In terms of the power series that you should have memorized for sure are only the 4 ones that I mentioned. but you should know the process of finding a Maclaurin series, and you should know the process of using the fact that you know a power series for some function to develop the power series of another function. We did that last time where we used derivatives to figure out power series, we used integrals to figure out power series, and we actually used algebraic manipulation to figure them out based on the power series of some generic function. But knowing things by heart, only those 4 that I mentioned. So I was supposed to omit some stuff here, so I wrote down the things that I actually want to mention. So here's one thing I'd like you to know about. There's something called a Taylor polynomial. So suppose f of x is a function such that f to the n of x naught is continuous on the interval ab, then the nth degree Taylor polynomial of f of x is, we usually call this p sub n of x, but it is just going to be a finite series. Let's say k goes from 0 up to n of f to the kth derivative at x naught over n factor over k factorial times x minus x naught to the k. So that basically means I'm just writing out a finite Taylor series here. So I start with well, f to the 0 evaluated at x naught plus f to the first derivative evaluated at x naught over 1 factorial x minus x naught plus f to the second derivative evaluated at x naught x minus x naught squared over 2 factorial plus dot 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 goes all the way up to the nth one. F to the nth derivative at x naught x minus x naught to the nth power over n factorial. So if you just take the first n terms of the Taylor series, we call that the nth degree Taylor polynomial of f of x. You can say it's centered at x naught. And x naught is just some number in the interval AB. So you can talk about a finite Taylor series, and it's called a Taylor polynomial. If you use n terms, go up to the nth power, you call that the nth degree Taylor polynomial. So I'll give you some time to take a screenshot there. 3, 2, 1. So for example, the 5th degree Taylor polynomial for f of x equals e to the x is, well, p sub 5. And so that's just going to be 1 over x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial plus x5 over 5 factorial. So it's just a polynomial with 6 terms. The highest power is 5, and that's my 5th degree Taylor polynomial. So it's just following the same pattern that I got from the Maclaurin series, centered at 0. And it's just that. So this is the 5th degree Taylor polynomial. And in the same way, like we were talking about a while ago, we can talk about a remainder term. So what you can think of as a Taylor polynomial, it's just a partial sum of a Taylor series. The nth degree Taylor polynomial is just the nth degree Taylor polynomial is just the nth partial sum of a Taylor series. That's one way you can think of it. And we know about, if we find the nth partial sum, you have to worry about there's a tail that's left over. There's an infinite sum left off at the end. And in the same way as that was called a remainder term for series, we actually use the same phrase when it comes to Taylor polynomials, Taylor series, right? So we have the Taylor polynomial is just the nth partial sum. The rest of the series is called the remainder term. So, So here you can have a Taylor series f to the n evaluated x naught times x minus x naught to the n over n factorial. And I can start writing that out. Well, this is f to the 0 plus f prime plus dot 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 going all the way up to the nth guy plus, then I can talk about the n plus first derivative at x naught plus dot 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 and this first part here is called the Taylor polynomial. And the tail part that's left over, going on forever, this is called the remainder term. And there is something called Taylor's formula. You can kind of think of this as a theorem on its own. Which basically says you can think of the remainder term is actually going to be f to the n plus 1 evaluated at c. X minus c to the n plus 1 over n plus 1 factorial for some c in AB. So it turns out that these infinite sums over here, and I'm not going to justify this, you can actually collapse it into one guy, just evaluating it at one particular point. And the reason why that's true is because of, it's kind of an extension of the mean value theorem that we learned from Calc 1. But that's basically what Taylor's formula. So Taylor actually derived the fact that the infinite number of tails, there's a specific x value that exists in the interval that you're looking at, that if you were to evaluate this, the n plus first term at that value, it will actually equal everyone else, which is interesting, but that's something else that you can know. What else do I want to tell you guys here? Actually, I think this is supposed to be x naught. And here's a theorem that can tell you about when the equality that I mentioned earlier in this class would work. There's a theorem that says the following. If your r to the n of x approaches 0 as n approaches infinity, then the Taylor series for f of x will converge to f of x. And now here's something I want to say, what that actually means. Okay. So the remainder term we can calculate with that formula. Now, it turns out if that formula approaches 0 as n approaches infinity, which doesn't always happen, if the remainder term approaches 0 as n approaches infinity, then the Taylor series will converge to f of x, i.e., they will be mathematically indistinguishable. Meaning, yes, they'll look different when you write them down on paper, but both the series and the function will behave exactly the same way under all mathematical operations. And we can write f of x equals its Taylor series. Which we could write as p to the n of x plus r to the n of x. So when I wrote that e to the x equals the sum of x to the n over n factorial, and I said cosine of x equals the sum from blah blah blah, you can actually think of this equal as a legitimate equal, meaning the right side and the left side are exactly the same, and they will behave exactly the same way. Whatever I can do to the thing over here, I can do to the thing over there. Any x value I can plug in over here and it works. I can put in the same value, x value over there, and it'll work. Like, these two are exactly the same thing, right? I can think of a function as an infinite series, provided that this thing is true. Which is crazy, kind of. Not going to prove it for you, but that's very nice. Your book actually proves it. But we ain't got the time or the manpower. So that's something that's very nice. And it turns out for the 4 examples that I gave you earlier, the 1 over 1 minus x, e to the x, the cosine of x, the sine of x, those guys will all converge to their Taylor series. It turns out you can find the remainder term as a formula, and if you take the limit as n approaches infinity of that formula, it'll actually approach 0. There are times when you can actually do this. You can find the Taylor series for a function, and the remainder term does not approach 0, which means the Taylor series and its function are different. That is possible. So f of x and its Taylor series may be different if r to the n does not approach 0. Right. So that's just a side note. I think there's a nice example. I believe if you do the Maclaurin series of f of x equals e to the 1 over x squared, if memory serves, that's the canonical example. So if you actually find the Maclaurin series of this guy, you will get 0, I believe, on any interval surrounding the origin. Well, I think it's a piecewise function. It's if x is not equal to 0, and it's 0 if x equals to 0. I remind myself, I don't remember off the top of my head, but I think there's an example similar to this. I'll remind you guys next time for sure. You'll never have to know this. It's just some interesting factoid that I'm throwing around there because I'm rambling and I'm getting too excited talking about this stuff. Okay, but there are possible things that you can do. There are times when you can construct the Taylor series and it's not going to fit its function on all intervals. However, sometimes something magical happens. The remainder term approaches 0 and your function is its Taylor series. I can think of these as exactly the same thing. All 4 examples that I told you about before will actually behave this way. The remainder terms do go to 0. So you can think of 1 over 1 minus x, e to the x, sine of x, and cosine of x as their Maclaurin series. They are indistinguishable. Whatever you can do to one, you can do to the other. Now, there's a theorem in your book, theorem 24, which technically I think we had to omit. We should omit. But it basically gives you an upper bound for your remainder term, so you can actually use that to figure out when the remainder term will actually approach 0. If that upper bound approaches 0, your remainder term will approach 0. But that's theorem 24. So. The theorem has a name. It is called Taylor's remainder theorem. So there's something called the remainder theorem, which tells you how to actually bound remainder terms of a Taylor polynomial. Once they're bounded and you figure out that the upper bound approaches 0, then by comparison theorem, this guy is also going to approach 0. I'm not going to write it out, even though it's really cool, because we didn't actually schedule any time for it, and it's not something I'm going to test you on, so I'm not going to actually talk about it further than that. But the main things I want you to is there anything else I want to tell you about in this section? No, nothing else I want to tell you about in this section. Okay. So, in 10.9, basically the takeaway is sometimes a function and its Taylor series are indistinguishable. This happens precisely when the remainder term of the Taylor series approaches 0 as you approach infinity. As n goes off to infinity, there is something called Taylor's remainder theorem that can help you figure out when this will happen. And it turns out that it happens for all the 4 examples that we did earlier. It happens for 1 over 1 minus x, it happens for e to the x, it happens for cosine x, it happens for sine x, it happens for a lot of other functions as well. But you can know that this is true. So you can think of these functions as exactly being equal to their Taylor series, or their Maclaurin series. So that's pretty neat. And let's move on. Let's move on to some fun stuff. So let's look at some applications here. This is 10.10. So 10.9, yeah, it's very hand-wavy. We're just giving lip service. Really, it's important stuff to know. It's just not important stuff for a Calculus 2 student to know, because no one's ever going to test you on that stuff. It's actually going to be, it's kind of hard to test you on that stuff at this level. Then here is something that we can test you on. Applications of Taylor series. I'm going to talk about 3 of them. 1, evaluating non-elementary integrals. 2, this is the most important one. That's one you're going to be tested on a lot. I'm going to talk about the binomial theorem. Binomial theorem. And I'm going to talk about Euler's identity. So technically these 2 are going to be skipped, but there's a lot of benefit to looking at going through them, as well as back when I taught Calc 1, I told my students that I'll tell them how to expand a square root. The reason why, if you think of this as that, you're actually missing, which is actually wrong. We know that we can't do that. But I mentioned that if you write this as that, you're actually missing an infinite number of terms. So I wanted to actually just quickly show you guys how you would actually expand this. Is there a way to actually expand a radical? The answer is yes. You can use Taylor series to help you expand a radical. And by applying Taylor series to the binomial theorem, we'll be able to expand things like this. And you'll see all the terms that it will generate. You'll actually be able to expand a radical now. So I wanted to show you that, even though probably not going to test you on that, but it probably won't take long for me to go through. It'll be a 5-minute kind of thing. Euler's identity also. So you are probably going to use Well, you're definitely going to use that in a class like differential equations and many other classes above this class. So figured I'd kind of show you guys what that is, and that's actually not hard to derive as well. So these are just maybe like a 5-minute discussion apiece. The thing that we mainly want to focus on in Calculus 2 is applying Taylor's theorem to evaluating integrals. There are many more uses, but we will ignore them. There's a nice application of Taylor's Taylor series to limits as well. Just another technique, kind of like how you have techniques like L'Hopital's rule and blah, blah, blah. You can actually apply Taylor series to limits. I might do a limit or two. That's a nice example there as well. But for the most part, we're going to apply this to evaluating non-elementary integrals. So let's jump into that. So the idea is actually not that complicated here. The idea is replace functions with their Taylor series. Which allows you to write a random function, random in the sense that it behaves well enough for us to actually apply a Taylor series idea to it, and it actually converges to a Taylor series. Replace the function with its Taylor series and do the integration term by term, because you can essentially write a function as an infinite polynomial, and integrating polynomials is easy, right? And we can approximate definite integrals using our series estimation theorems that I covered with you 2 classes ago. So that's the idea. So I give you an integral that, using all the techniques in the world, you can actually find an antiderivative for the integral that I give you. So the question is, the problem is sometimes we want to be able to actually evaluate such integrals, especially if they're definite integrals. They might have applications. How do you go about evaluating these integrals? Well, replace them with their Taylor series. Of course, you want to know that they actually converge to their Taylor series, that you can think of the function as the Taylor series. Integrate term by term, and then you can estimate it using a series estimation theorem. Let's actually just jump into an example. There's not really much to talk about conceptually other than this. So let's actually jump into an example. A specific one in mind here. A. Find the Maclaurin series for sine of 2x squared. B. Estimate this integral. The integral from 0 to 1 over 10 of sine of 2x squared as a sum of two fractions. Three. Give with explanation. An upper bound on your estimate above. So copy that down, take a screenshot or whatever. Okay, let's begin. All right. Let's make sure, because I know I've been rambling for a while, everyone's quiet, want to make sure everyone's still alive and listening. Maybe someone can chime in. How do I find the Maclaurin series for the sine of 2x squared? Ideas?
Maybe you could start with the derivatives?
Yeah, the derivatives.
Sure. That's if you wanted to derive it from scratch. So you could go f prime. What would the derivative of that be? What's the derivative of sine of 2x squared?
4x cosine 2x squared.
Right? And then if you go to f double prime, now you're going to need a product rule. So you would do differentiate the 4x, leave the cosine of 2x squared, then leave the 4x, multiplied by the derivative of cosine 2x squared, which is another 4x sine of 2x squared. Then you can kind of see that this is actually going to start ending up being very annoying, right?
Wait, what if you like make your 2x squared as your x and kind of like rewrite it as sine x, but replace the x with 2x squared?
Yeah, so that's a much nicer way. There are going to be times, the only time when you have to do this, like, too hard. What I would say is only do something like this. If there is no known series that can help, right? So I give you some random function, like someone asked earlier about tangent of x. If I ask you about the tangent of x, then yeah, you kind of would have to bite the bullet and go through this sort of process to kind of carefully figure out the coefficients. However, we know about the sine function. We know about a series that gives us the sine function already. There's no need to actually go through this process all over again. So in general, I wouldn't really just jump for that. First of all, once you know those four main series, the series for 1 over 1 minus x, the series for sine of x, cosine of x, and e to the x, you will automatically know how to deal with anyone who, one, is just some sort of algebraic manipulations of these, or two, is an integral of this, or a derivative of some of these. You'll automatically know how to actually find those guys. So I would actually use that to your advantage. So how I would approach this one is we know that sine of x is equal to the series n goes from 0 to infinity of minus 1 to the n of x to the 2n plus 1 over 2n plus 1 factorial, right? And it turns out the remainder term of this guy approaches 0 as n approaches infinity. Sine x is that. It is this. They're exactly the same thing. So this means that my sine of 2x squared, all I have to do is just plug in 2x squared. So my sine of 2x squared, I'm just going to go to this formula and I'm going to plug in 2x squared. And that's my Maclaurin series. In fact, I can actually write this out a little bit nicer. This is minus 1 to the n times 2 to the 2n plus 1 times x to the 4n plus 2 over 2n plus 1 factorial. Now, if you look at this coefficient here, you can probably imagine how annoying it would have been for you to figure out that that guy is going to actually give you the Maclaurin series. Second of all, it doesn't even work for all n. It only works for guys that look like 4n plus 2. It means that the guys that look like 4n, 4n plus 1, 4n plus 3, 4n plus 4, those guys all give you 0. It'll be a really nasty pattern to actually have to figure out. So we don't need to do that. We can just use the known Maclaurin series for the sine and actually just plug in to both sides of that equation. Any questions on that part?
Wait, Professor, how do you know it goes to 0? Like when it's 4n or 4n plus 1?
Because it would just, because if you look at the kind of numbers that you can represent as 4n plus 2, it's not all integers that can be represented like this. First of all, if you look like 4n plus 2, you're always going to be even. There's no odd number that you can write as 4n plus 2, right? So you're definitely skipping some guys, right? So your powers here, your powers of x, when your n is 0, it's 2. Then when your n is 1, it jumps to 6. Then when your n is 2, it jumps to 10. Then when your n is 3, it jumps to 14. Which means that all numbers in between these guys were skipped, right? There is no x to the 1 power, or x to the 3 power, or x to the 4 power, or x to the 5 power, etc. Right? It's skipping a lot of powers, right? So pretty much you'll realize what happens if you were to do this directly. You realize for all the other powers of x, the coefficients are going to give you 0. You're going to skip over them. And then for these particular powers, this is going to be the pattern that gives you the coefficients, which would be hard to actually figure out. So the power of x can tell you what terms you're skipping, what terms you're actually hitting, right? We'll only be able to hit even numbers that have this form. But the moral of the story is you don't actually want to derive this directly. If I give you a function for which you already know a power series for that function, just manipulate that series to get to the version of the function that you want. So that would be the answer here. Let me write that down so I don't forget it. Okay, so that's that. So now the second part was estimate using a sum of two fractions, estimate that integral. Now the first thing I want you to appreciate is that this integral, if it was indefinite, you couldn't actually do it. There is no element, it's the antiderivative is not elementary, right? There is no antiderivative that we can come up with that when I differentiate it, I would get sine of 2x. And I don't mean it's hard to do it, I mean it's impossible to do it, right? You can't actually find that antiderivative, not in terms of the functions that we're used to seeing, called the elementary functions. I can write it as a polynomial or a trig function or a log or an exponential or a radical or any algebraic combination of these or a rational function, right? So the general antiderivative here is impossible to find. So you can't find the antiderivative of that and plug in these numbers. So we're kind of out of luck computing this integral directly. This is, as we call it, this is a non-elementary integral, meaning it has no antiderivative. Not in the traditional sense, anyway. We kind of just make up a function that we call its antiderivative, but we can't actually express it in the language of math that we've used up to this point. So that's the first thing. So we can't compute this directly. Let's approximate it, because we know in the real world, practically speaking, everything is an approximation, right? So we're going to approximate this, and we want to approximate it specifically with two fractions. So how would you go about actually doing that? Anyone want to chime in with an idea? How much time do I have left? We're running short on time, so maybe quickly.
Integrate using the series that we found.
Integrate using the series that we found. I can think of the integral of this as that, the integral of this series. The series we found was minus 1 to the n, 2 to the 2n plus 1, x to the 4n plus 2 over 2n plus 1 factorial. So I literally swapped this guy out. Now, because we know that we converge absolutely, that's the important key. Sine of 2x squared converges absolutely to the series. I'm allowed to switch the summation and the integral sign. So I can go from a situation where I'm thinking of it as this to a situation where I'm thinking of it as the sum of this. The fact that I can swap these two and move the parentheses this way is a consequence of the rearrangement theorem. We're only allowed to do that if we have absolute convergence, which means now I just have to worry about integrating this. Now how would I integrate that?
I think it would be, well, if you would like leave everything constant.
Okay.
Except for where the x is, so it would be negative 1 to the n times
Negative 1 to the n, 2 to the 2n plus 1 over
x to the 4n plus 3.
2n plus 1, da da da. So that's a constant, and then?
And then you multiply by x to the 4n plus 3 over 4n plus 3.
4n plus 3 over 4n plus 3. Add 1 to the power, divide by the new power. That's the integral. Now, of course, we're going to plug in 0 and 1/10 here. Which is equal to, if I plug in 1/10, that's going to be pretty much the sum . One over 10 to the 4n plus 3 over 2n plus 1 factorial 4n plus 3 minus, when I plug in 0, I just get 0. So it turns out that that is actually the integral, the definite integral. This is actually the answer. Now, you might not be able to express that in a nice way, but the question was to actually estimate it with a sum of two fractions. So what we're going to do is we're going to say this is approximately equal to now actually take a snapshot here because I want to clean the board a little bit and try to rewrite this. 3, 2, 1, snapshot. Okay, so what we have so far is that the integral from 0 to 1/10 of sine of 2x squared is equal to the series I can even write this another way, move this over. 2n plus 1 factorial times 4n plus 3 times 10 raised to the 4n plus 3. We have that. Now what we're going to do is we're going to approximate this using a finite number of fractions. So what I'm going to do now is I'm just going to plug in some n's. So what I can do here is I can plug in n equals 0. Now if I plug in n equals 0, I would get, well, that's going to give me 1. This will give me 2 divided by 3 times 10 cubed. This is 4n plus 3. So that is the first fraction. Plus, now let's plug in when n equals 1. Now if n equals 1, I would get a minus sign here. Here, this gives me 2 cubed over n equals 1 here, I would get 3 factorial. N equals 1 here, I would get 7. N equals 1 here, I would get 10 to the 7. Now I'm going to calculate another term, and you're going to, hopefully that will be a hint as to part C. But you'll eventually, hopefully you'll figure out how we can answer part C by me and calculating this other term. If n equals 2, I would get a plus sign. On top, I would get 2 to the 5th power over 5 factorial times 11 times 10 to the, I'm plugging in n equals 2, 8 plus 3, 10 to the 11. So here's your answer to part B. I can approximate this integral by just adding these two fractions right here. Right? Now, of course, in general, I could do it by adding more fractions, but the problem specifically stated approximate it as a sum of 2 fractions. Now, normally, there will also be an instruction that says something like, oh, you don't have to really simplify your answer. So leaving it in this form is fine. You don't have to actually calculate, oh, 3 times 10. Well, this one's not so bad, but you don't have to calculate, oh, 10 to the 7 times 3 factorial. Like, don't worry about it. You can write it like that. That is your answer. Let me copy that down here in case we need it later. Is everyone with me so far? It's kind of getting heavy, but hopefully you're following somewhat. So yeah, give you a moment to take a snapshot of this. 3, 2, 1, boom. So the idea is replace this guy with his series. You already memorized the series for sine of x. All you just do is plug in 2x squared in place of x in that series. Then you switch the integral and the summation, integrate term by term. Everything else except the x to the 4n plus 2 was a constant, so you just add 1 to the power, divide by the new power. Then you plug in the 1/10 and the 0, you ended up with this series. Now you just plug in some n values, as many n values as you're required by the problem. Now I did calculate an extra one, which is probably going to help you talk about part C. So what's in the green box is our approximation of that integral, part C. Anyone wants to tell me what that is? Yeah. Yes, we are a bit over time, but we're wrapping up now. I'll leave the other two guys to do. Okay. Give an upper bound on the above. Any idea on what that could possibly be?
Isn't the third term that you calculated the supposed to n plus 1 term?
It's the third term. It turns out that the error between these first two guys is going to be less than or equal to the third term. Now, it also mentioned that you should give an explanation, so why would you say that? By the way, what is that number? Now, you don't have to know this, but I'm actually interested how close we actually got. Do you know how close this actually is? This is 2.424 times 10 to the minus 13. Isn't that crazy? Okay, so this is actually point 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 2, 4, 2, 4. That's how close we got to the actual answer just by taking the first two fractions for this particular series, for this particular integral. Meaning, Wolfram alpha could calculate this integral and give you an answer up to 12 decimal places by just adding those two fractions that I just told you. Which now you kind of know how Wolfram alpha does it. When you ask Wolfram alpha to find the definite integral of something that's impossible to integrate, or you ask most computer algebra systems the definite integral of something that's impossible to integrate, this is what they do. They convert that thing to a series, they add up enough terms to get the error to be smaller than the amount of decimal places that they want to produce on screen, and then they just they might be able to get a lot of accuracy just by adding up two fractions or three fractions. So you type in this integral in Wolfram alpha, you press enter, and it pops up in a second of what the answer is. And you're like, how did it do it so fast? It literally only had to add two fractions. Sure, it had to convert it to a series, integrate it, then add two fractions, but a computer can do that really quickly. So yeah, the area is actually this. Now, what is the reason So the person who said just look at the third term as the upper bound, what is the reason here?
Oh, I cannot tell you. I really don't know.
Well, why did you say the third term?
Because it looks similar to like the old approximation theorem, like the s minus sn has to be less than or equal to a of n plus 1. That's why.
Right, so that's it then. That's the reason.
Oh.
But that's the reason. Notice that your integral was an alternating series. We know how to approximate alternating series. In fact, we know specifically how close a partial sum of an alternating series is to the whole answer. When we looked at the integral in general, the answer was an alternating series. So by the alternating series approximation theorem, the third term gives an upper bound to the error of the first two terms. That's it. It was actually an alternating series. So if you want to know how good an approximation is the first two terms, the third term tells you. If the problem asks you to add up, write it as a sum of 3 fractions and asks you how good is the approximation, all you have to do is calculate the fourth term, and that's going to tell you. It works because it was an alternating series as your answer. So we're out of time. We will wrap up there. Here's something I would leave you guys with to try for Thursday. First of all, go over this. So take a snapshot of this. 3, 2, 1. Let me leave you with something to ponder and try for Thursday. Because this is a very nice problem. It's something that's more than likely to show up on a test or the final. So for Thursday, 1. Repeat the above for, let's say, the integral from 0 to 1 of e to the minus x squared. Right? That, again, something that's impossible to find the antiderivative for. Find the area under that curve from 0 to 1. That actually tells you a way that, well, it's indicative of a way that you can use in probability with the bell curve, finding the probability that something lands between 0 and 1. We'll probably talk about that. But actually just repeat the above for this guy. So, find that integral approximated with 2 fractions. Tell me how close your approximation is to the actual value of that integral. 2. Use series to prove Euler's identity. It's going to be really cool if you actually get this to work out. Of course, there are multitudes of websites that you can look up that actually show this, but it'll be really nice if you actually do it yourself, and it's not super difficult, so it's not, has a little bit of algebra to it. So Euler's identity is the following equation. It says e to the I. Now, it's represented by I theta, but you can think of it as an x here, is equal to cosine theta plus I times the sine of theta, where I is your imaginary unit, it's the square root of minus 1. This is a very important equation. It gives rise to one of the most beautiful equations in all of mathematics. A lot of math people think it's the most beautiful equation in all of mathematics. But yeah, from this, you can realize that e to the I pi is going to be cosine of pi plus I sine of pi, which means that you have e to the I pi equals cosine of pi is minus 1, or in other words, e to the I pi plus 1 equals 0. right? From this equation, you can get to this equation, which is pretty cool. Maybe I'll talk a little bit about that next time. But actually try to prove this equation. It's actually not that hard to do it using series. So try that for next time. We'll wrap up there. We'll go continue to be safe. Keep working hard though. And unless there are any questions before we wrap out? Okay, so we'll stop there. We've gone over time again. Well, enjoy the rest of your day. I will see you guys back here, same place, same bad channel on Thursday. And yeah, and also I do have office hours via Zoom. I sent out the, we don't have class on Thursday? Why? What's Thursday? They sent an email? Was it today? Oh, I'll check. I'll check to make sure. That's strange. Oh, which reminds me, you guys should actually do what I asked. I don't remember if I mentioned it. I mentioned it to somebody. Go check the academic calendar again because a lot of things are updated on the calendar. So you guys might be right. We might not have class on Thursday. But I'll see what's going on. I'll be sure to check the calendar before then. In the meantime, try this. Pretty cool stuff. And we'll talk more about that, look at some more applications of Taylor series next time, and we'll probably move on from the series section to something else by the next class. So do that, and yes, you guys look at your calendars. Look at the academic calendar. A lot of things have been updated on the academic calendar because of everything that's been going on. So the last day to drop classes and all that stuff, it's been pushed. I think a lot of things have been changed. So make sure you look into that. We may or may not have class Thursday based on what someone is saying. I will verify that for myself. I'll definitely send you guys. I'll definitely send you guys confirmation. That being said, if you do want to see me during office hours, I'll still have those on Thursday. I sent you guys the link earlier, so we'll do that. Until then, I will see you guys next time. Take care. Yes, I will send a confirmation email about the whole thing. Good night. Have a good one as well. Bye, everybody. Okay, just tuck the kids in. So good night to you as well. Have fun. Maybe try some of these problems. They'll be really, really cool if you can get them to work. Cheers.